lectures 2 and 3 of organic contaminants in the subsurface. In lecture 1, we talked about some basic environmental properties of organic contaminants. We talked about the subsurface in terms of sources and plumes, and also about the potential for partitioning of the organics between important phases in the subsurface. These phases included the NAPL phase, both residual and free, the dissolved phase, the vapor phase, and the sorbed or solid phase. Today we want to proceed into the transport of contaminants in the subsurface that involve these phases and environmental processes. When we talk about contaminant transport, we really have to think about 4 types of processes. The first, and arguably the most important, is advection. That is the movement of the contaminant along with the flowing groundwater. The second process is dispersion, the slow, minor mixing of the contaminant with uncontaminated groundwater. As you can see by this cartoon, dispersion has 2 real effects. It tends to dilute the contaminant plume, especially near the front, but it also tends to move some of the contaminants a little bit faster than they would have been given just simple advection. The third process, retardation, is the interaction of the contaminant with the solid. The contaminant spends some time on the solid and therefore moves less quickly. The last group of processes, reactions, involve biological or chemical reactions which affect the organic contaminants. So when we look at contaminant hydrogeology for organic contaminants, these are the processes we need to deal with. So in lectures 2 and 3, we'll deal with these processes. We're going to do this by making use of videos that already exist on the Hidroplan website. As you can see, the first 4 sections are really dealing with groundwater movement, advection, which we think is the dominant process. Then we have videos on dispersion and retardation. We'll add some additional material that's relevant particularly to this course. So here's the relationship of the videos to the different processes. What we want to do now is go to the Hidroplan website and show you how to navigate to find these videos. So here we are at the home page of Hidroplan. Direct your attention to the right-hand side. We have some material that's available on this site. Here's material for our course that we're involved in now. But what I want you to do is have a look at the material that's below it. There are 7 lectures shown here. There's actually 8 lectures that I want you to look at as part of our lecture 2 and 3. To access all 8, let's hit more videos. Then we can scroll down through material that's available. Course on remediation. Some general basic information. Here we are. This is the section on monitored natural attenuation. As you can see, there are 8 items here, and I want you to have a look at these as part of lecture 2, lecture 3. Let's just have a look at the introduction. Takes us to this list. Again, let's look at introduction. And here's the video. Let's play the first part of it.
Welcome to the second section of organic contaminants in the subsurface environment. Today we're going to start talking about processes that affect the dissolved contaminant plume. But we're going to do this in a slightly different way. We're going to talk about it as a remedial technology. The technology is termed monitored natural attenuation.
So we're going to discuss the processes in these videos in terms of a technology. Let's go back to lecture 2-3, pick it up from there. Well, welcome back. We now have the videos located. We can make use of them. So for Lecture 2, we expect that you'll have a review of the first 4 videos, and we'll deal with those in the tutorial to do with Lecture 2. For Lecture 3, review the last 4 videos, and we'll discuss that in the tutorial related to Lecture 3. So here's some of the added material that we find is useful as you proceed through those videos on the Hidroplan website. First process that we'll deal with is advection. Advection is dealt with by hydrogeologists using Darcy's law. That is, the flow of groundwater, the flux, is equal to the minus K, which is hydraulic conductivity of the material, cross-sectional area through which the water is flowing, and the change in hydraulic head over a certain length. The negative sign comes from the fact that groundwater flows from areas of high head to low head, and this is covered in the Hidroplan videos. Note that sometimes we refer to something called the specific discharge by dividing Q by A. This gives us dimensions of velocity, but this is really not the average linear groundwater velocity that we're probably interested in. We can simplify Darcy's law as being equal to KIA with a negative sign, where I is this gradient, the change in head over some length. The actual groundwater velocity is given by this equation, and you can see it involves porosity. And that's because water tends not to flow through the solids, but it only flows through interconnected pore space. So the velocity has to be adjusted for that. So make sure when we talk about groundwater velocity, we're using this last expression and not the specific discharge concept. So average linear groundwater velocity, it's a function of the porous media because hydraulic conductivity and porosity are functions of the porous media. Sometimes we define something called effective porosity because not all the pores are active in transport. There might be dead-end pores. This value is typically half or maybe 90% of the volumetric porosity. In many cases, it's used to adjust models to more clearly represent field situations. It's real, but it's often very hard to estimate what the effective porosity really is. The key issue really is that real porous media are heterogeneous. That is, the properties like hydraulic conductivity and porosity are spatially variable. An interesting textbook was published in 2008 on remedial hydraulics. And it's the first book that really emphasizes the role of heterogeneities in contaminant transport. I think it's a very good addition. Here's a quote from that book. So at the scale of site remediation, the scale we're interested in, heterogeneities at a smaller scale are not only significant, but they have a controlling influence on the behavior of the contaminants as well as any chemicals we may be adding through water or vapor. So heterogeneities are extremely important to us. And of course, they're very difficult to assess. So again, hydraulic conductivity varies spatially. Real aquifers have considerable heterogeneity, and they're at all scales, from the pore scale to the kilometer scale. The difficulty for us in contaminant work is that our measurement of the heterogeneity is rarely done at the small enough scale that's important for contaminant transport. Illustrate it with this cartoon. We are measuring the aquifer property hydraulic conductivity through a slug test. It's conducted in a well that has a screen that's 2 meters long, and we would have to assign an average hydraulic conductivity to that unit that we're testing. We would then calculate an average linear groundwater velocity from that hydraulic conductivity and assume that the flow through that 2 meter segment of the aquifer is as calculated from that K. More often than not, in fact, the unit is not consistent. It's heterogeneous, even over 2 meters. So what would happen if there was a thin 20 centimeter layer that was much more permeable than the other units? Well, we would end up with this situation. We would find that for most of the unit, the actual velocity is a little bit less. However, in one unit, where most of the contaminant transport is occurring, the contaminant would be much further away from the source than we anticipated because of the higher hydraulic conductivity. Now, this is very difficult to deal with for hydrogeologists. We have no way of knowing that that layer exists unless we do measurement at a very fine scale. But we have to be aware that, in fact, those layers do exist. So our conceptual model has to be robust and acknowledge these sorts of uncertainties. And they'll be very important in dealing with contaminant transport and with some remedial technologies. Okay, as we go through the videos, we'll come to the video on badly monitored plumes, and we're sharing some of our experience of monitoring with you in these videos. Unfortunately, the first 3 minutes of that video depict a field site which is not the correct one. So we'll replace that with the following information. We were talking there about the need to monitor a plume and how easy or difficult it is. How much data would you usefully use to determine where the plume is and where it's going? We used as a reference this information that was produced in 1999. They laid out a minimum monitoring network that you might use at a petroleum hydrocarbon contaminated site, and also a more typical layout. Likely the more typical layout would happen after you've done the initial layout and seek some additional confirmation. The important wells are an upgradient well to find out what the background water is like, a well near the source so we clearly have an idea of what the source is like, and then at least 2, if not more, wells down gradient to define what the concentrations are like going down gradient, and also 1 well beyond the plume to make sure that we are monitoring that the plume in fact has not got that far. Sort of a sentry well. Well, here's that network again. The difficulty is that dispersion is a weak process, especially transverse to flow. This diagram shows a conceptualization of a plume where the plume spreads out laterally to a certain degree. What would happen if the plume was smart and in fact stayed narrow as we actually anticipate plumes to stay narrow? Well, I would think we would get the same information in the wells for this smart plume as we did in the original conceptual plume. That is a decline in concentrations with a very low concentration in the leading edge well and no concentration down gradient from that. The plume is simply smart. It deviates a little bit in flow direction, deviation that we probably can't recognize in the field, and is going past the monitoring wells without being seen. This would be a failure of monitoring. Well, does this occur? Well, again, here's a real plume. This is from Vandenberg Air Force Base in California. This plume is not only narrow, but it makes a left-hand turn. Heterogeneities in the hydraulic conductivity, in the permeable units again. Do you think this plume is well monitored? Well, no, it's sort of making a left-hand turn, and it's going to avoid any of the monitoring wells we've shown on this diagram. So that brings up the very difficult question. When is monitoring sufficient? And that's a site-specific issue. Your experience will help you with that. And it generally leads us to believe that where we recognize a significant risk, we may have to enhance the monitoring to adequately deal with the risk of contaminants moving in areas we didn't really expect. And in the Hidroplan videos, we share some experiences along that line with you. The next 4 areas, dispersion, retardation, and reaction, are fairly well covered in the videos that Hidroplan has on its website. These videos are working towards a remedial technology called monitored natural attenuation, and we give you a case history near the end of how you might apply this sort of fate and transport information to decide whether natural processes are adequate to remediate sites. So we've shown you the links between our interests and the Hidroplan videos. We just want to add one summary to that. So this is a summary for lecture 2 and 3. Really what we're doing in these lectures is dealing with the 4 processes that control the transport of organic contaminants. So we can always ask ourselves, are these processes good ones or bad ones? Well, advection, I think, is fairly clearly bad. has the potential to take a contaminant from a source to a receptor, and therefore it's generally bad and has to be defined fairly well. Dispersion, is it good or bad? Well, it brings about dilution. However, you can see from this cartoon that it actually moves a small amount of contaminant faster than advection. So that's maybe not a good thing. Retardation. Well, again, it looks pretty good. It's slowing up the contaminant. That gives us longer time to react. The liability is that those contaminants that have been attached to the solids come off later, and the contamination in the aquifer will persist much longer, certainly at a lower concentration, but the length of time that we may have to worry about contamination increases. Reaction. Well, surely that's good. We're getting rid of the contaminant. But what would happen if the reaction is producing a more toxic and more mobile chemical than the product that we started out with? This happens with chlorinated solvents. Trichloroethylene is converted to the more mobile and more toxic vinyl chloride. That, in fact, would be bad. These processes are quite complex, and their outcomes are not always clear. In Lecture 4, we'll now move back to the source and talk about NAPLs, and then we'll carry on for remediation in these sorts of systems. Thank you.